Welcome back. In this part, dealing with heat transfer, we begin a discussion of the second of the three types of methods by which heat moves from one location to another. We've finished in the previous parts discussing heat transfer by means of the emission of electromagnetic waves. Now we'll talk about heat conduction. The conduction of heat through a wall or along any substance is much like a row of dominoes tipping over. One end of the substance is heated, and the rapidly moving atoms at that end collide with their neighbors, and the process is repeated down the length of the substance. A number which characterizes the speed with which the dominoes tip over is called thermal conductivity. The greater the thermal conductivity, symbolized as K, the more rapidly heat is transported or conducted, we say, along the length of the material. I show here three representative thermal conductivities: air for air, glass, and aluminum. Notice the frightful units associated with thermal conductivity: watts per meter Celsius degree. Air has a very low thermal conductivity. Heat travels through a barrier of air very slowly compared to, say, aluminum or glass. Heat travels through glass 48 times more rapidly than it does through an equal thickness of air. Now, let's discuss the equation that one can use to calculate the number of joules per second that pass through a wall or a barrier, let's say. That quantity will be symbolized as R, standing for rate, the same symbol that was used in our discussion of infrared radiation. Watts are the units, joules per second, same as a watt. Well, I show here a wall whose thickness is X and whose face area on either side is A, measured in square meters. Likewise, X, the thickness of the wall, is measured in meters. On one side of the wall, maybe it's facing a bedroom, the air temperature is T subscript 1. On the other side of the wall, perhaps it's in contact with February morning air, cold air, the temperature is T2. Now, we will have use for the quantity shown here, which is the absolute value of the temperature difference shown here in long form. The equation shown in this box, the rate equation, represents the number of joules per second that travel from the bedroom into the morning air, measured in watts. It's the thermal conductivity, K, times the face area, the same on each side. Face area inside the bedroom, same as outside, times the absolute value of the temperature difference. Now, the temperature difference, you may recall in an earlier part I, is measured not in degrees Celsius, not with a superscript circle or zero in front of the C symbol, but after. So it's Celsius degree are the units for temperature difference. So the rate is Ka, absolute value delta T over X. The units are in watts. Let's work a simple example. Quite simple. We have a block of glass. I show it just in 2 dimensions. Its face area is 6 square meters. And the thickness of the glass, it's a window, let's say, is 2 centimeters. But make sure you understand we have to convert that into standard units, meters, eventually. Well, we ask the question, what is the rate? That is to say, how many joules per second pass from bedroom air out into February morning air? Well, we use the equation shown here, Ka delta T, absolute value. There's your K taken from this table, measured in watts per meter Celsius degree. Area 6 meters squared. 20 Celsius degrees is the difference in the temperatures, 30 versus 10. The absolute value of that difference is just 20. And then we convert 2 centimeters into meters in this way. And final result can be obtained, but first let's see if the units work out as they must. When the dust settles on this calculation, the final unit, the surviving symbol for units, better be watts, W. Well, let's do some cancellation here. We have a meter squared in the numerator of this expression, but there's a meter in the denominator there and another denominator meter. So the meters units cancel. That M and that M downstairs, canceling the M squared upstairs. And the Celsius degree there cancels a Celsius degree downstairs. And the unit that is left is a W. The actual number itself, I calculate as 5,760. 5,760 watts. Final answer. Let me double check to make sure that I have it correct, and I believe it is good to go. That concludes this very elementary introduction to heat conduction. We will work a few more problems involving heat conduction in the next part.